Welcome everyone to the first online lecture for Math 239. As you saw in the introduction video, the first half of this course is on problems in enumeration, or in more plain English, counting problems. Let's just look at a few of them before we start. Counting problems will often start with the words how many, so here's 4 such problems. How many ways can we put 6 objects in order? So I give you a set of 6 objects, a box containing 6 objects, I tell you to put them in order. How many ways can you do that? Problem 2. How many ways can you write a binary string of length 10, so that's 10 digits in a row, each one is a 1 or a 0, such that you're not allowed to write a 1, then a 0, then a 1. So any binary string is allowed as long as it doesn't contain 1, 0, 1 inside it. How many ways can you do that? The third problem, how many ways can you make change for $1? So if we're back in a world where people are still using money, I'm asking how many ways are there to split $1 into smaller coins. So you could have 4 quarters or 10 dimes or some combination of them, and you want to know how many ways to do that. We might see later in the course there's actually different ways to interpret that question with different answers. And finally, if you like gambling, how many ways can you deal a full house in poker? So there's some number of ways that you can be given 5 cards. How many of them will give you a full house? So that's 3 of one card and 2 of another. Now these are all quite different problems, but a major goal of this course will be to build an algebraic machine that can solve all of these problems and many more. So we're going to use ideas that are both combinatorial and algebraic to solve problems like this. The algebra will be the focus, but for the first week we're just going to be looking at more basic combinatorial notions to solve counting problems before we start pulling out all the stops. We'll start by talking about how choosing elements from 2 different sets can correspond to both a product and a sum mathematically. We'll start with products. Here are 2 finite sets. A is a set of 3 animals and B is a set of 4 vehicles. And suppose I ask the number of ways you can choose an animal from A and a vehicle from B. So you have to make 2 choices, one is an animal, one is a vehicle. Now hopefully it's not too hard to see that number of ways I can do that is equal to the size of A times the size of B, which is 12. In fact, there's a standard set theoretic way of saying the same thing, and that is to say that the 12 possible choices you can make here, in fact, are exactly the elements of the Cartesian product of the sets A and B. Now the Cartesian product is defined to be the set of all pairs little a, little b, where little a belongs to the set A and little b belongs to the set B. And this is something you see all over mathematics. The reason it's called the Cartesian product is because it's the same product which turns the real numbers into the xy plane, the Cartesian plane. Now with the Cartesian plane the sets are infinite, but what will always be true for finite sets is that if you have the Cartesian product of sets A and B, the size of that product is the product of the sizes of A and B. And therefore the number of ways you can make a choice from A, then a choice from B, is equal to the size of the Cartesian product, which is equal to the product of the sizes. Let's move on to sums. We'll start with the same 2 sets, A, a set of 3 animals, and B, a set of 4 vehicles, and we'll ask the same question with one word changed. This time I'm going to ask, how many ways can I choose an element of A or an element of B? Now this is even an easier problem. I've got 3 choices that I could have made from A, and I've got 4 choices I could have made from B. So of course, the number of ways I can choose something from A or something from B is the sum of those 2 numbers, which is 7. Now just like in the previous example, there's a nice set theoretic operation that describes what's going on here. This time, instead of being the Cartesian product, it is the union of the 2 sets. It's hopefully obvious that the set of all choices I could have made here is equal to the union of the set A and the set B. That is the set of all x, such that x is either in A or in B, or both. Now we have to be slightly careful when we're talking about the size of the union of these 2 sets. It is true that the size of the union of A and B is the sum of the sizes, but that's not true for all finite sets, it's only true for disjoint sets. If you have something that's both in A and in B, the size of A union B is going to be smaller than the size of A plus the size of B. So to summarize these last 2 slides, when I'm talking about combining choices using AND, I want to make one choice and another choice, that's going to turn into a problem involving a product of sets and therefore a product of sizes. If I want to combine two choices using OR, I want to make one choice or another choice, then that's going to turn into a union of sets, and if the sets are disjoint, a sum of sizes. Now these two ideas are simple, but they're actually enough to solve counting problems involving a number of different objects. I'll show you two examples now. The first is subsets. Here is a simple counting question. If I have an n-element set S, how many subsets does the set S have? To solve this problem using the techniques we just learned, we need to think about a subset X of S as the result of making a sequence of choices. For each element U of S, we make the choice whether that element will go into the subset X or if it won't. In other words, specifying a subset of S is the same as choosing an element from the two-element set in, out, n times, once for each element of S. There are two options for each choice, and since I'm making n separate choices, I'm really combining them using AND. So to compute the total number of possibilities, I have to multiply the size of the set in, out by itself n times, once for each choice. This gives a total of 2 to the n possibilities, and so that's the number of subsets of an n-element set. This idea doesn't just give us a way of counting subsets of a set, it actually gives us a way of putting subsets of a set into correspondence with a different type of object. The best way to see this is with a small example. Let's look at the set S equals A, B, C. We've just seen the number of subsets of S is 2 to the power of the size of S, which is 8. But we did this by putting the subsets of S into correspondence with triples, where each element of the triple is either in or out. For example, the subset X equals A, B, C, which is equal to S itself, would correspond to the triple in, in. The subset X equals AC would correspond to in, out, in, and the subset X equals the empty set would correspond to out, out, out. This is assuming we've put the elements of S in order, A, B, C. The reason that S has 8 subsets is because there are 8 possible triples. This general idea of associating objects of one type with objects of another type is very important in lots of counting problems, and we'll be seeing it again. Let's look at another example. Again, suppose I have an n-element set S, but instead of wanting to count the subsets, I want to count the number of ways I can put the elements of S into order. To say exactly what I mean by this, it's easiest if I give you a small example. A 3-element set S, such as the set A, B, C, will have 6 ways of putting them into order. We'll call them lists. Here are the 6 ways. We could take A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, or C, B, A. Just like when we counted subsets, we can view constructing a list like this as making a sequence of choices. Here, I had 3 choices for the first element of the list, then I had 2 remaining choices for the second element of the list, and 1 remaining choice for the third element of the list. Since I'm making 3 separate choices, again I'm combining them using AND, so I multiply the number of possibilities for each choice to get the total number of possibilities. This gives 3 times 2 times 1 equals 6, which is the number of lists. And this is the only idea we need to solve this problem in general. If I have an n-element set S, then to construct a list of the elements of S, I have n choices for the first element of the list, and then I have n minus 1 choices for the second element, and so on, right down to only 1 choice for the last element of the list. Again, we're combining these choices using AND, so to compute the total number of possibilities, I have to multiply all these numbers, n times n minus 1 times n minus 2, and so on, all the way down to 1. This is the number of possible lists of an n-element set. The number of lists of an n-element set is so important in combinatorics that we have special terminology and notation for it. We write n exclamation marks to denote the product of the numbers from 1 up to n, and we call it n factorial. For example, 1 factorial is just equal to 1, 2 factorial is 1 times 2, which is 2, 3 factorial is 1 times 2 times 3, which is 6, 4 factorial is 24, and so on. This sequence of numbers actually grows very quickly, faster than any exponential function. The way I've defined factorials looks like it only makes sense for the positive integers. However, it's actually convenient often to set 0 factorial to be 1. This might look strange, but it will actually turn out to be very natural and exactly what we need. It's probably a good thing to think about why 0 factorial should be 1 as opposed to 0 or anything else. Now we just saw how to count lists of a set, but in fact the ideas that we used work equally well to count partial lists of a set. We define a length k partial list of a set S to just be a k-tuple S1 up to Sk of distinct elements of S. So a length k partial list consists of k elements of S in order, and they all have to be different. For example, if S is the 4-element set A, B, C, D, then the partial lists of S with length 2 are shown below. There are 12 of them, AB, AC, AD, and so on. Note that AB and BA, they contain the same elements, but because they're in a different order, they're different partial lists. If we want to count partial lists of length k in an n-element set, then we can use the exact same technique we use to count lists. We view constructing a partial list of length k as making a sequence of choices. We have n possible choices for the first element of the partial list, n minus 1 for the second, and so on, right down to n minus k plus 1 choices for the last element of the partial list, sk. It really is n minus k plus 1 choices for the last element, not n minus k. It's important to watch those off by 1 errors. Just like with lists, if we want the total number of possibilities, we multiply all these numbers of choices, and we get n times n minus 1, right down to n minus k plus 1 as the number of length k partial lists of a set S with n elements. Now there are 3 things I want to mention about this formula. The first is what happens when k is bigger than n. This isn't a very interesting case of the counting question because I'm asking how many partial lists of length k there are in an n-element set where k is bigger than the size of the set. Of course the answer to this question is 0. For instance, there are no length 5 partial lists in a 3-element set. There just aren't enough distinct elements to have one. The nice thing about our formula is that it gives the right answer even when k is bigger than n. The reason for this is that if k is bigger than n, the product n times n minus 1 and so on contains an n minus n factor, so it's equal to 0. That means the formula correctly tells you that there are no length k partial lists in an n-element set if k is bigger than n. It's always nice to have a formula that works even outside the usual range of cases. The second thing is that there's a nice way to write this formula that doesn't involve dot dot dots. We can observe that the product of n down to n minus k plus 1 is the same as the product of n down to 1 divided by the product of n minus k down to 1. The denominator will cancel with all the stuff in the numerator that we don't want. And we can rewrite this in terms of factorials. The top of the fraction is n factorial and the bottom is n minus k factorial. This is a nice compact way to write this formula. Note that it only works if n is at least k, otherwise the factorial on the bottom is negative, so it doesn't make sense. However, if n is equal to k, the factorial on the bottom is 0, and that's one of the reasons we like 0 factorial to be equal to 1. And finally, a point that applies not only to this problem, but to every problem that we solve in this way. When we described a partial list as the result of a sequence of k choices, it was important that every possible sequence of choices would give us a partial list, but also it was important that no 2 sequences of choices which are different would give you the same partial list. If we had that happening, then we would have counted the same partial list more than once, so our formula would have been wrong. We've seen a few things today, so I'll summarize them now. The first is that we can solve counting problems by decomposing them into individual choices. If I have to make a choice 1 and a choice 2, then that will turn into a product in a formula. If I have to make a choice 1 or a choice 2 and they correspond to disjoint sets, then that will turn into a sum in a formula. The second thing we did is apply these ideas to solve counting problems for a few different objects. We saw that if you have an n-element set S, then S has 2 to the n different subsets. It has n factorial different lists, n factorial meaning 1 times 2 times 3 all the way up to n, and that it has n factorial over n minus k factorial partial lists of length k, provided n is at least k. Next lecture, we'll see how to combine some of these ideas to count subsets of S of a given size. Thank you for watching.